Hi, this is part 2. This is a follow-up to the first part where I explained what it means for a function to be homogeneous. And then in the situation where you're solving a first-order differential equation, where the coefficient functions on dx and dy are both homogeneous of the same degree, you can substitute in place of y, put vx, and in place of dy, put vdx plus x dv, and you get a separable differential equation, which you can then solve by separation of variables. So, as promised, here's another example of how that works. Here we're solving the equation x dx plus sine squared of y over x times the quantity y dx minus x dy equals 0. Now, to see if this fits the kind of thing that I was talking about, let's multiply some things out so we can see, okay, what is the coefficient on dx and what is the coefficient on dy in this equation? So with this multiplied out, we have an x dx, we have a y times sine squared of y over x times dx, minus we have an x times sine squared of y over x times dy equal to 0. So the coefficient for dx altogether is x plus y sine squared of y over x, and the coefficient on dy is minus x times sine squared of y over x. And these two coefficient functions on dx and dy are both homogeneous of degree 1. I'm not going to go through exactly why that is. Hopefully you can see that, or if not, you can work it out for yourself. If you still can't figure it out, contact me and I'll try to explain it. But these are both homogeneous of the same degree, degree 1. So that trick is going to work here. I am going to substitute in, I'm going to introduce the new variable v, which stands for y over x. So that means y is going to turn into v times x everywhere it appears, and dy is going to turn into v dx plus x dv. So after making that substitution, I now have x plus vx times sine squared of, and of course, y over x would just be v. Or it would be vx over x, which is just v. So we got that times dx, plus we have negative x times sine squared of v times the dy turns into v dx plus x dv. And that's equal to 0. Now multiplying things out, that gives us x dx plus vx sine squared v dx minus vx sine squared v dx minus x squared sine squared v dv equals 0. Now right away I can see one thing we can do that would simplify things quite a bit, and it is to take the plus vx sine squared v dx minus the same thing and just add them together and get 0. Now I can't promise you that this sort of neat collapsing or canceling will always happen. Sometimes things get a lot more complicated than this. It is always guaranteed to be separable, but it's not always guaranteed to be something that simplifies down really nicely. But here it does. We just have x dx minus x squared sine squared v dv equals 0, or get the v part on the other side, x dx equals x squared sine squared v dv. Now we still need to separate the variables. We want there to be only x stuff in front of the dx and only v stuff in front of the dv. And that means we need to get the x squared out from in front of the dv. So just divide both sides by x squared. When I do that, over here, the x divided by x squared simplifies to 1 over x in front of the dx. And over here, we just divided away the x squared, so we're left with sine squared v dv. Now we have separated the variables, and we're ready to integrate both sides. The integral of 1 over x dx equals the integral of sine squared v dv. And in order to integrate sine squared, you could just look this up on a table of integrals, or you could remember the trigonometric identity that sine squared of any variable is equal to 1/2 times the quantity 1 minus the cosine of 2 times that variable. So by using that identity, I transform sine squared into something that's easier to anti-differentiate. So now integrating both sides, the integral of 1 over x dx is the natural log of the absolute value of x. And then we have the integral of 1/2, which is 1/2 v, because we're anti-differentiating with respect to the variable v, minus the integral of 1/2 times the cosine of 2v is 1/2 times another 1/2 times the sine of 2v. And we've got our constant of integration, plus c. Now, don't forget, we're sort of done with the integration part, but we still need to unsubstitute. Remember, the v here and here is really y over x in disguise. So if I rip the disguise off, what we really have is ln of the absolute value of x equals 1/2 times y over x minus 1/4 times the sine of 2y over x plus c. Now, we're probably not going to be able to nicely solve this for y and get it as y is some explicitly defined function of x. We may just have to leave it kind of all jumbled up like this and say, okay, this gives us the solution where y is a function of x implicitly defined by this equation. But if you want to clean things up a little bit, there are a few things we could do. We could get rid of some of the fractions by maybe multiplying both sides through by the number 4. So 4 times the natural log of the absolute value of x equals 4 times 1/2, or 2 times y over x, minus 1 times the sine of 2y over x, plus, and then 4 times an arbitrary constant would really just be another arbitrary constant. So instead of saying this is 4c, I could just say it's plus c. Another thing we could do is we could multiply through by x and get 4x times the natural log of the absolute value of x equals, and then 2y, because y over x times x would just be y, minus, and here we can't cancel out the x because it's part of something that we're taking the sine of. So we have to just leave this as x times the sine of 2y over x. Unless you want to mess around with some trigonometric identities to try and rewrite that somehow, but I don't want to mess around with that. And then the 4c, or just the c, gets multiplied by x. And I'm just going to leave it like that and say that gives us our solution. Like I said, it's not always easy or even possible to nicely get it solved for y, but you can say, okay, this gives us the solution to our original differential equation, at least implicitly defined. So that's that example. I could show you more. I'm not going to, unless you really, really want me to. If there's a strong desire for more examples or for me to explain anything in greater detail, let me know. But that's it for this video and this particular technique for solving differential equations.